I show you in this video how generating functions can be used to prove recurrence and transience properties of one-dimensional random walks. In the previous video we covered simple random walk. We defined it to be just a simple random walk, so plus minus 1 steps with probability p and q independently. And we defined the hitting time of level 1, which is tau plus, so the first time that the walk is at level 1. And then we concluded that it has a nice generating function, which is of this form, 1 minus square root of 4s squared pq over 2sq. This happened in the previous video, so that's the generating function. Okay, so now the first question I want to address here is that time finite? What is the probability that tau plus is finite? What is the probability that the random walk ever finds himself or herself, the walker ever find themselves at level 1? What is the probability of that? And if we have a generating function, then it's easy to find what that is, because everyone hopefully remembers that take the generating function at s equals to 1, and that exactly gives us what the probability that tau is finite is. Okay, so all I need to do is take a look at this generating function and plug in s equals to 1. So this will give me 1 minus square root of 1 minus 4pq over 2q. And that's something we have seen a very similar computation before. So let me repeat this computation here. Okay, now there is this trick with 4pq, 1 minus 4pq, which is very nice. I claim that 1 minus 4pq is a full square, because it's 1 minus 4p 1 minus p, or 1 minus 4p plus 4p square, which is 2p minus 1 squared. Because 2p minus 1 square indeed gives me 4p square minus 4p plus 1. So 1 minus 4pq is 2p minus 1 squared. What happens if I take a square root of a square? It will give me the absolute value of the quantity. So this is 1 minus the absolute value of 2p minus 1 divided by 2q. And clearly 2p minus 1 is 0 when p is a half, so p smaller than a half or larger than a half will make a difference. Okay, so let's take a look at p smaller than a half. When p is smaller than a half, then 2p minus 1 is negative. So the mod of 2p minus 1 is actually 1 minus 2p. So I'm going to put here 1 minus 2p over 2q. And that just gives me 1 minus cancels, so the two ones cancel. It's positive 2p over 2q, or p over q. So when p is smaller than 1/2, then this is p over q, which is indeed a probability, because p is smaller than half means q is larger than half, so p over q is a number smaller than 1. When p is larger than a half, then 1 minus, then actually 2p minus 1 is positive. The absolute value doesn't do anything with it. So I have 1 minus 2p minus 1 like this over 2q. And that gives me positive 2 and minus 2p, so that's 2 minus 2p over 2q. But 1 minus p is actually q, so on top I just have twice of that. So that gives me 1. So when p is larger than 1/2, then it's 1. When p is smaller than 1/2, then it's p over q. And you can easily check that actually both cases work when p is equal to 1/2. And then here is the interesting feature, that this thing here, when p is smaller than 1/2, this thing can be, and in fact it is, strictly smaller than 1 if p is strictly smaller than 1/2. What does it mean to have p strictly smaller than 1/2? If p is strictly smaller than 1/2 and therefore q is strictly larger than 1/2, then we have a drift to the left. There is a tendency to go more to the left than to the right. The walker prefers the left direction more than the right direction. In this case, it is not probability 1 that the walker will ever hit level 1. There is a positive chance that the walker starts off to the left and never comes back to hit level 1. Okay? They might come back to the origin, but will never come back to hit level 1 with probability 1 minus p over q. Okay? With that probability, tau plus is infinite. Tau plus is infinite when level 1 is never hit. Okay? So if there is a drift to the left, then there is a positive probability that level 1 will never be hit. Okay, let's now find the expected value of this quantity. What is the mean of tau plus? Once we have the generating function, we should be able to find the mean. And straight away a little warning sign: do not differentiate the generating function if tau plus can be infinite with a positive chance. Okay, so if p is smaller than or equal to 1/2, if p is smaller than or equal to 1/2, then with a positive chance, namely 1 minus p over q, tau plus is equal to infinity, and then the expectation is infinite. If there is a positive chance for a non-negative random variable to be infinite, then the expectation is infinite. Okay? Do not differentiate anything in this case. When p is less than or equal to 1/2, e of tau plus is infinite. End of story. Now, the interesting bit, of course, is when p is larger than 1/2 or larger than or equal to 1/2. Let's take it strictly larger. We'll see in a second why. When p is larger than 1/2, then expectation of tau plus is equal indeed to the derivative of the generating function at s equals to 1, because in that case the probability of tau being finite is 1, so we can differentiate that, and the generating function itself is here. So I just need to differentiate this function, take it s equals to 1, and see what I get. Okay, so let's differentiate the function, 4s squared q squared in the denominator, and then let's differentiate the square root. Now, derivative of square root is 1 over 2 square root. So this is, and I have a minus in front, so this is minus 1 over 2 square root. I'm not going to write out square root, right? So square root is this. That's what square root is. Okay, 1 minus 4s squared pq. That's the derivative of square root. However, the square root itself is a complicated function of s, so I have to look into the inner function, the derivative of the inner function, which gives me a negative 8spq. Okay, so that is the derivative of the inner function. That I multiply with 2sq, which was my denominator, and from that I subtract the original numerator times the derivative of the denominator. So 1 minus square root times the derivative of 2sq, which is 2q. Okay, and I have to plug this in at s equals to 1. Okay, so let's plug it in at s equals to 1, and also let's simplify with a couple of things we can. So what happens to the square root at s equals to 1 is that the square root, let me write this out again separately. So if I take the square root at s equals to 1, that will give me, remember, that will give me the mod of 2p minus 1. However, I'm in the case p larger than 1/2. Okay, so p is larger than 1/2. Ah, you don't see that. So the square root will give me the mod of 2p minus 1. That's what I put down here. However, p is larger than 1/2 in the case we're interested in. So this is simply 2p minus 1. The square roots will just become 2p minus 1 everywhere. Okay? And let's see what else we can cancel with. So we have a square root here. We have actually a total of, let's cancel with a 2 for the moment being. Let's just cancel with a 2. So I have a minus will cancel, so that's a plus. 1 over, I'm going to kill this 2 here. I'm going to cancel out a 2 from the 8. So I'm going to make this a 4 and this a 2 and cancel out that one as well. And then I have the 2 minuses cancel out. S equals to 1. And I'm also going to cancel out one of the q's. I'm also going to cancel out one of the q's. So one of the q's is also gone. And now it's getting a bit complicated, but let's hope that everything works out fine. So 1 over 2p minus 1 for the square root. Okay. Then the minus is gone. I'm left with a 4. I'm left with PQ. S equals to 1, I don't need to write that down. And then S equals to 1, I don't need to write that down either. 1 minus square root. So the square root is 2p minus 1. And then the 2q is gone. And I have downstairs a s square is just 1. I have a 2 and a q. So I have a 2 and a q there. Okay. Okay, so 1 over 2p minus 1 downstairs here. A 4p, and let me not yet write down the q, because if I look at here carefully, what I notice is that I have a positive 2 minus 2p. 2 minus 2p is just 2q. So I can actually cancel out the 2q. Let's cancel out the 2q. And that makes a 2 out of here. So that actually is only a 2. Okay, so it's 1 over 2p minus 1, 2p. And then I have a minus 2q, which is cancelled out, so that just gives me a minus 1. Okay, and so let's make this into a common denominator. It's a little bit algebraic, but let's do that. So common denominator is 2p minus 1, and I have 2p minus 1 of that. Because 2p minus 1 over 2p minus 1 gives me this negative 1 there. Okay, and then finally, let's break this up. 2p minus 2p is 0, minus is a plus 1 over 2p minus 1. That's my answer, and I can make this even nicer a little bit if a p minus 1, so I have a p and a p minus 1, I can rewrite the p minus 1 as negative of q. Q would be 1 minus p, so this is p plus p minus 1, which is p minus q. And notice that p is larger than 1/2, so this is indeed a positive nice number. Okay, this is the expected time to reach level 1 if there is a drift to the right. If p is larger than 1/2, if the walker has a drift, a tendency to go to the right, then this is how long it takes on average. Notice that this will go to infinity, so this blows up. If we take p closer and closer from above, p is larger than 1/2, don't forget that. P is larger than 1/2. If we take p closer and closer to 1 from the above, which also means, of course, that q is 1/2. Which also means that q is going closer and closer to 1/2 from below. In that case, this difference goes to 0, and the expected time blows up. So for a simple symmetric random walk, this expectation would be infinite. If I take a simple symmetric random walk, then this is infinite. Okay? Alright, so that was the expected time to reach level 1 from level 0. And now I want to do something even more. I want to show you one more calculation with the return time to the origin. So let's do the return time to the origin. Okay, let's do that in another color. Return to the origin. So to this order, I'm going to first define tau minus to be the infimum of times when Sn is minus 1. The first time the walker finds themselves at minus 1. Okay? As a comparison, tau plus was the first time the walker is at plus 1. This is the first time the walker is at minus 1. Alright? Now, what is the difference between these two? Well, if I flip the whole thing in a mirror, then of course tau plus becomes tau minus and tau minus becomes tau plus, except for one difference, that I flip the left and right probabilities. If I flip everything into the mirror, that makes tau plus into tau minus and vice versa. However, P and Q gets flipped. So for that reason, I can immediately find the generating function for tau minus. It is going to be almost the same as the one for tau plus, except that P and Q will be swapped. The role of P and Q is swapped. So by symmetry, the generating function of this quantity, namely expectation s to the tau minus, is going to be this same formula. So 1 minus square root of 1 minus 4s squared pq. Notice pq is symmetric in pq. Okay, so I was just copying this part over. However, here I only had q, so now I will only have p. So that's my generating function for tau minus. Okay, now the other quantity I want to show is but before that I'm gonna take yet another color. So the other quantity I want to introduce is tau 0. Tau 0 is going to be the first time, at least one, when Sn is 0. And so this is going to be the return time, first return time to the origin. This previous one was of course the hitting time of level minus 1. This one was the hitting time of level minus 1, and this is the first return time to the origin. Notice an important point here, that n is at least 1, so we do not count s naught equals to 0. In the original definition of the random walk, we said s naught equals 0. This is not counted here. Okay, so this is the first time after 0 that the walk returns to the origin. Each of these guys can be infinite, and in some cases they will be infinite with positive probability. Okay, that's the case when, for example, the walk never returns to 0. And in fact, let's find out the generating function for this one here, which I'm going to call P naught. So what is expected S of tau naught? And the way to do that is very simple, because again I'm going to do a first step analysis. What is the expected S of S to the tau naught, given that the first step is to the left, which happens with probability q, plus same thing, expected S to the tau naught, given the first step is to the right, which happens with probability p. Okay, and let's again think this through. It's now we have quite experience with that. The claim is that tau naught, given the first step, is to the left, is easy to calculate. In distribution, it's going to be what? So here's the picture again. Here's my random walker. If the first step is to the left, that takes 1 unit of time to do. And once we find ourselves at -1, in order to return to the origin, I need to wait until the first time I can step one unit up. So I need to wait this amount of time in distribution, the first time that I can move one step to the right. Okay, the level 1 hitting time, the first time I can hit from level -1 to level 0, which of course is the same in distribution. The first time I can hit level 1 from level 0. So in distribution, I have another tau plus time here, and so this is going to be tau plus. Let me put a prime here because it's an independent version of the real tau plus. Okay, so it's just a copy. And of course the same thing will happen with the first step being to the right. If the first step is to the right, then I wasted one time to do that, and now I find myself at level 1. Level 1, from there I need to get back to the origin. How long does it take? Well, this is what I called tau minus. I'm going to put a prime again because it's an independent copy of that tau minus. Alright, and so therefore I can proceed here and just say expected s to the 1 plus tau prime plus, okay, times q, and expected s to the 1 plus tau prime minus times p. These are the two terms I have, okay? And each of them will come with a factor s, because there is this factor s in front, this one here, which is not random, and I can factor that out, so sq, and then I find the generating function of tau plus, and I can factor out the s, I have a p, and then I find the generating function of tau minus, and those I actually know already, so I'm just going to plug them in. Sq times generating function for tau plus is here, so 1 minus square root of 1 minus 4s square pq over 2sq, and sp, the generating function for tau minus, is up there, so I'm just plugging that in. Remember, it was just the same as the one for tau plus, except I had to swap the role of p and q. So I can just copy the formula over, except I need to swap the role of p and q, so this is going to be 2sp. And something quite nice happens. Sq cancels here, sp cancels there. It's a 1/2 of the same quantity twice, so I end up with this very simple, or rather simple formula, 1 minus square root of 4s square pq. Okay, so that's the quantity I find. All right, now the usual questions arise, of course. Let's find out whether the random walk return time to the origin is finite and what the expectation of it is. And the way to do that is going to be pretty much the same as before. So let's do this. Okay, so the first question, what is the probability that tau naught is finite? What is the probability that in finite time the walker comes back to the origin? And if I have the generating function, all I need to do is plug in s equals to 1. So let's do that. Plug in s equals to 1 here. So that's a 1 minus square root of 1 minus 4pq. Okay, 1 minus square root of 1 minus 4pq. At s equals to 1, that's what I get. Now remember that the square root with s equals to 1 was just 2p minus 1 under the mod. Okay, and again I need to do cases. So the two cases are if p actually is larger than or equal to 1/2, and if p is smaller than or equal to 1/2. If p is larger than or equal to 1/2, the mod doesn't do anything, so I have 1 minus 2p minus 1, and that just gives me, that's a plus, that just gives me 2 minus 2p, which is 2q, which is indeed less than 1, because p is larger than or equal to 1/2 means that q is smaller than or equal to 1/2, twice q is smaller than or equal to 1. Okay? And if p is less than or equal to 1/2, then the 2p minus 1 is negative, so the mode changes sign, and I have this, and that just ends up to be 2p, which is again a probability, it's smaller than 1, because p is less than 1/2. Okay? Notice that this thing is smaller than 1 if p is not 1/2, which also means q is not 1/2, and is equal to 1 if p is equal to 1/2. When p is 1/2, then also q is 1/2, then these two are 1. So the cases are called transient for the probability of ever hitting the origin again, ever returning to the origin, is strictly less than 1. That's the case called transient. And when it's equal to 1, then this is called recurrent. In particular, we proved that simple symmetric random walk, p equals to 1 exactly, was simple symmetric random walk. Simple symmetric random walk in one dimension is recurrent. Okay? However, if it has a drift, if it's not symmetric, then it's transient. When we have a drift, there is a positive chance, namely related to the drift, so either 1 minus 2q or 1 minus 2p, whichever is a probability, there is this chance that we never come back to the origin. And then finally, let me find the expectation of tau naught. So what is the expected time to return to the origin? And so straight away, again this remark from before, straight away this is infinite if we have a positive chance of never coming back. So this is infinite if p is not 1/2. If p is not 1/2, either smaller or larger than 1/2, there is a positive chance that tau is equal to infinity, and the expectation of non-negative random variable in that case is automatically infinite. No need to do anything more. So let's then do the calculation if p is equal to 1/2. Let's do the calculation if p is equal to 1/2. Okay, so here is the generating function again. P naught of s is that. Let's plug in p equals q equals 1/2. If p is 1/2, then so is q. And then pq is 1/4. So the generating function itself is 1 minus square root of 1 minus s square. 4 times 1/2 times 1/2. They cancel out, so the 4 cancels out with pq, and I just have this generating function. Okay, so let's differentiate and take s to 1. So what is the derivative of this? And then let's take s to 1 afterwards. So there is a minus sign, there is a square root, so it's 1 over 2 square root. However, there is an inner function in the square root, namely 1 minus s square, that differentiates to minus 2s. So the answer is, the minus 2 cancels, the answer is s over square root of 1 minus s square. And now I need to take this at s equals to 1. So E of tau naught is actually this at s equals to 1. Now there is a slight problem here. If I take s equals to 1, then this thing doesn't make sense. So in fact, what I need to do is take a limit as s goes up to 1 from below. S approaches 1 from below of s over square root of 1 minus s square. And the reason is that if you look at everything we did, the generating function makes sense on the closed interval 0, 1. It still makes sense at 1. However, the derivative blows up at 1, as we'll see in a second. And still the derivative as we go from left, it still makes sense and is still going to give me the expectation. If you don't believe that, then just go through how we looked at the expectation from generating functions, and you'll see that even in the case when you cannot define the generating function above 1, still the expectation is given by this derivative in the limit. So what happens in this limit is that when s is smaller than 1, then the square root is perfectly fine and is a positive number, but it goes to 0 from the positive direction. S is close to 1, so when you divide s, which is close to 1, by a small positive number, then it blows up. So the expected return time to the origin is infinite. Okay? And therefore, what we can say is that not only simple symmetric walk is recurrent, it's actually called null recurrent. That's the expression in Markov chain theory. If a process comes back to the origin almost surely, but it takes an infinite expected time, then we call this process non-recurrent. Okay? Simple symmetric random walk. Remember, all of this is simple symmetric random walk because p is 1/2, right? So all of that is simple symmetric random walk. Simple symmetric random walk returns to the origin almost surely with probability 1, but it takes an infinite expected time. And when it's not symmetric, when p is not 1/2, then it does not come back to the origin almost surely, only comes back with a positive probability which is less than 1, and then it's called transient.